Okay, hi folks. In this video I'm going to be going over all the waves questions I could find on the November 2021 IB DP Physics HL exam, paper 2. So we start off with the longitudinal wave traveling with a speed of 340 meters per second. That's the speed of sound, so it's probably a sound wave. And we are looking here at the oscillations of a single particle in the medium, its displacement versus time. And we have to first calculate the wavelength. Okay, so we can't read off the wavelength directly because this is just the simple harmonic motion of a single point. But what we can read off is the period. So that's going to be 4 milliseconds. Remember to pay attention to the units on the axes. So we have the period, 4 milliseconds, and then, of course, most of you would be looking up the wave speed equation, which makes good sense to use because the frequency is the reciprocal of the period. So wave speed is wavelength over period. We have the wave speed, we have the period, so we can find the wavelength very easily by just multiplying these two together. And that gives us the correct answer. Okay, then we have to determine the magnitude and the direction of the acceleration when time is 2 milliseconds. Okay, so we're looking at this time value, and you can see so the particle at that time has displaced itself to the left, right? Negative displacement is to the left, and it's displaced itself the most to the left. So it has the largest acceleration, which is going to be pointing to the right, because in simple harmonic motion, acceleration is opposite and proportional to the displacement. So the acceleration is to the right. Because it is displaced to the left. Okay, and we have to find the magnitude. Okay, and then we have to remember that for simple harmonic motion, the magnitude of the acceleration is always omega squared times x, just the magnitude. Okay, so I'm just working with positive quantities here. And the omega angular frequency is 2 pi over the period, and x is the displacement, which we can read off as -6 micrometers, remember. So basically we just have to sort of plug in everything. We have 2 pi over 4 microseconds, have to square that. And then we have to put in 6 micro. Did I say micro before when I meant milli? Now it's micro. And plug all that in, you get around 15 meters per second squared. There you go. Okay, then there's another wave in the medium, and they are going to superpose and create one resultant wave. So remember the principle of superposition. And they're a little bit out of phase here, so we have to state the phase difference. So remember that 2 pi radians corresponds to 1 period. Okay, and the period was 4 milliseconds, and you can see these two waves, they're 1 millisecond out of phase, and 1 is a quarter out of 4. So we just have to take a quarter of 2 pi radians. That's pi over 2 rad. That's the phase difference. Identify time at which the displacement is 0. Okay, well, we know we have to add the two separate displacements to get the net displacement. And we can see around 1.5 we get displacements that are equal but opposite. One wave is displacing the medium 4 up. The other wave is displacing the medium 4 down. They're going to add up to 0. So it's at 1.5 milliseconds where the displacement is 0, but it's not always going to be 0. You know, this point is oscillating as a result of this superposition. But at this time, it's definitely 0. and estimate the amplitude of that oscillation at this point. And what we have to do is look for the largest possible sum we can get, which happens at this point. And if we're getting a displacement of 4 from each wave at this point, then the amplitude of the resultant wave is going to be 8 micrometers. Now, for some reason, the IB, they haven't drawn these sinusoidal graphs perfectly accurate. So it turns out if you actually draw these sinusoidal curves, then they intersect at a little bit more than 4 micrometers. So the amplitude is in reality more like 8.5 micrometers. But okay, they are just asking you to estimate it, and for some reason they haven't drawn sort of perfectly accurate sinusoidal curves here. Standing sound wave is established in a tube closed at one end, open at the other. Half open tube. Period is T. Okay, so we know this is a longitudinal standing sound wave. You have to, of course, be able to look at this and immediately write down that's the second harmonic standing wave, because the first is with a node on the closed end and one antinode at the open end. But here we have an additional node. And this is 3/4 of the wavelength we can see. So the whole tube is 3/4 of the wavelength. And they gave the wavelength to us, 1.2 meters. So we get the final answer. There you go. Then we have a particle in the tube, and it is at the open end, so equilibrium position is over here at the open end. State and explain the direction of the velocity at that time. Okay, so as you can see, when time is 0, it has its displacement all the way to the left, because it's a negative displacement, maximum negative displacement. So it's kind of all the way over to the left when t is 0. And then when time goes on, it's gonna move to the right. Displacing itself from negative to positive displacements, and it's going to be all the way on the other side in half a period, and then it's going to swing back again. So it's performing these horizontal oscillations here around equilibrium. So you can see that when time is 1/8 of a period, it's on its way over to the right. It still has a negative displacement, but it's moving to the right. So we can state that the velocity is to the right, and that's just a statement. You don't really need to explain anything. Well, yeah, sorry, you have to state it. That's the statement, and then we have to explain it, and then we can say because it is displacing itself from the left, where it has a negative displacement, to the right, positive displacement. There you go. Draw on the diagram the standing wave at that time. Okay, well, we can see that after 1/4 of a period, it's going to be at the equilibrium, and all the particles in the wave are going to be at their equilibrium position after 1/4 of a period. So we just draw a nice horizontal line here. Every single air molecule is going to be in its equilibrium position after 1/4 of a period. Okay, so now we're moving on to question 3, and the first part of this question was just an electric field question. So we're just going to move on to question B, which is a simple harmonic motion question. And so what they've done here, they have these two charges, Q. So I think they were two positive charges, Q. And then you have a little tiny charge, Q, which is negative -2 microcoulombs, which is now placed here. So that's going to be, attracted to both of these positive charges. So it has a net electric force pointing straight down. And they tell us that when x, its vertical displacement from the horizontal there, when that displacement is very small compared to d, then the net force is around 150x, approximately 115x, okay, the net force. Now then, why is it going to perform simple harmonic oscillations? Well, you can see because force is proportional to the displacement, and it's also going to be opposite because the electric force is always going to be pointing towards the equilibrium when x is 0. So even if it goes below the horizontal, then because these are two positive charges, it's going to get attracted upwards again. So it's going to be oscillating sort of up and down here. So we have to just write that in words, and you can write that in many different ways. We can focus on the force here, so we're going to write that the force is always directed towards the equilibrium, which is x equals 0, and it is always proportional prop to the displacement, because they give us the formula where that is the case. So if the force is opposite and proportional to the displacements, then so is of course the acceleration, and that is really the defining condition for simple harmonic motion. Then we have to calculate the period of oscillation, so we have to now use the fact that, okay, F force is, of course, ma. The net force is ma. That's going to be 115x. We get that from what they gave us. And then the acceleration is 115 over mx. And why do I do that? Because we have to remember that the constant in front of x for simple harmonic motion is always the angular frequency squared, right? So this is omega squared is 115 over m. So from that we can get, we're looking for the period. We know the period is hidden in the angular frequency, because omega is 2 pi over t, which is therefore equal to the square root of 115 over the mass, which they give us. And then we can just rearrange and find the period, which is 0.29 seconds. Okay, so kind of like standard simple harmonic motion question. Very, very standard. Got to really know this. Okay, then we have a Doppler effect question, topic 9.5. State what is meant. Okay, so it's one of those things you have to maybe sort of practice parroting off the definition of the Doppler effect. So we could write that it is the change in observed frequency of a wave due to the relative motion of a wave source and an observer. Okay, so change in observed frequency, and it's due to the relative motion of a wave source and an observer. Okay, so we have a plate performing simple harmonic motion, has that frequency, amplitude, maximum speed. Okay, straightforward application of this formula, max speed omega amplitude. Okay, I just know this by heart, but it's also kind of hidden in the data booklet equations in many different ways. And we are given the frequency, omega is 2 pi frequency. So we just plug that in. Remember that the amplitude is in centimeters, convert to meters, and we get the right answer, around 20 meters per second. Okay, then an interesting question, that oscillating plate. now sort of reflects some sound waves that is approaching it. And we have to determine the maximum frequency of the sound that is received back at the source after reflection. So maximum frequency. So we have to see how we can maximize the Doppler effect here in the direction of increasing frequency. Well, we could say, well, first of all, the sound, we want the plate to be moving towards the sound with its largest velocity, because then the plate is going to be receiving the highest possible frequency. So let's first write that down. So plate receiving a highest possible frequency. So we look up the correct equation in our formula booklet, right? So when we have a moving observer, so the plate is the observer. Imagine there's a microphone on the plate. We want it to be moving towards the source as fast as possible. So we know the frequency is going to increase. So is it the plus or the minus? Well, we need to have a factor in the bracket here that is greater than 1. We know the frequency has to go up, so I need to use the plus sign because I need an increase in frequency, which we know happens when we are moving towards the sound source. So 2400, and speed of sound is 340, and the maximum possible speed of the plate, we just calculated that was 20 meters per second. So 340 plus 20 is 360 over 340. Okay, so that's going to be the largest possible frequency that the oscillating plate is observing. But then that is then going to reflect off the plate, and that becomes the source of some sound. And then we want it to be moving, of course. Well, wait a second. Yeah, so the plate is actually now a moving source, right? Because when the sound reflects off the plate, it is moving. So suddenly the plate becomes a moving source. Okay, so we now have the source as the stationary observer. It's a bit confusing. The source is now receiving, and it is going to be receiving a higher frequency of that maximum frequency we just calculated, right? So f prime is going to be undergo the Doppler effect because it's a moving source. Okay, so the wavelength is going to bunch up in front of it and all that. So now it's a moving source, so we use the right formula. Is it the minus or the plus? Well, we know again that the frequency has to increase, so I need a smaller denominator, and then we can plug everything in. So f prime is this, and then I have v 340 over 340 minus 20, 320. This cancels out, and you actually just get 2,700 hertz. 2,000, that's a 7, not a 2. Whoops. 2,700 hertz. Okay, that was an interesting problem. And then it continues with multiple slits here. So we have to, of course, know these diffraction patterns, interference patterns quite well. We have 4 slits here. So of course we have to remember that we will, between the primary maximum, we're going to have 3 minima then. And we're going to have 2 secondary maxima. It's always like that, right? N slits, you get n minus 1 minima, n minus 2 secondary maxima. Now they're going to be increasing the number of slits. Okay, so that means we're going to get many more minima between the primary maxima. Separation, width of all the slits is going to stay the same. They're all being illuminated. So we have to remember that for the diffraction gratings, which this is, the maxima, they all occur at the same location as if you just have 2 slits. Okay, so this d sine theta equals n lambda. The constructive interference condition is the same for diffraction gratings. So even though I add more slits, the primary maxima are going to be at the same angular position, so they stay the same. And the width of the primary maxima, so when we add more slits, what happens is that we get narrower primary maxima, okay, and then they get more intense and they get more narrow, okay, so the width of the primary maxima will decrease. They get more narrow when we add more slits, and the intensity of the primary maxima increases, right, because we have more slits means more wave sources, which means we get more amplitude added together at the constructive interference points, which means you have a higher intensity. But the secondary maxima, they actually decrease in intensity. So the intensity of the secondary maxima, that intensity also decreases. So it gets darker and darker between those brighter and brighter primary maxima. Okay. Now that is actually that. Okay. So see you later.